Testing, 1, 2. Testing, 1, 2. Okay, so let's do lecture 7 now. I want to begin as usual with a review of what we did last time. We were discussing discrete time homogeneous Markov chains. Again, discrete time, discrete state. And introduced the Chapman-Kolmogorov equation, which is shown right here. Basically, it says if you're going to go from state I to state j, on the way from I to j, you'll pass to an intermediate state k, some arbitrary intermediate state. So you go from I to k and k to j in a total of m steps. The first q steps from I to k, the remaining m minus q from k to j. So this very simple equation describes the possible paths you could have taken from I to j in m steps. This is the matrix equivalent of that. Basically, you have q steps and then m minus q steps. Now, in particular, if you set q to a particular value, m minus 1, you get what's called the forward Chapman-Kolmogorov equations. Just replace q by m minus 1. If you set q equal to 1, you get the backward Chapman-Kolmogorov equation, and both are used. Often the backward is the one we use. We then went from homogeneous to non-homogeneous. And in that case, you can't simply talk about a quantity Pij, but you talk about Pij at time m for state I and time n for state j, because this transition probability from I to j depends upon what time it is, not only on the difference in the times. In that case, the Chapman-Kolmogorov equation looks like this. There's the forward and the backward equations. And from that, we're able, in fact, to talk about a new function, which we called H. It's a matrix of these time-dependent state transition probabilities over from time m to time n. Chapman-Kolmogorov gives us this equation. Not surprising. You just multiply the matrices. First, the first q steps, then the m minus q steps to get to h of m and n. And we also got the forward and backward equations. We then went to a more interesting case, a more difficult case, continuous time, non-homogeneous. That's a complicated set. It's still discrete state. It's a chain, not a process. And in that case, we defined the transition probability from state I to state j from time s to time t. Remember, it's continuous time now, not from m to n, but s to t. Chapman-Kolmogorov equation looks like this. It turns out that this matrix can go to basically a continuous time version. What is it? It consists of the elements I just defined, the time-dependent Pij's. That leads to a relationship among the h's, obviously given this way. You're going from S to U, then U to T. We then defined a particular S and T, namely this matrix P of T is a matrix of elements, which means at time T, you're in state I, and delta T seconds later, you're in state J. Remember, continuous time, you can move at any instant in time. The forward equations look like this. And this quantity q we defined as the limit of this thing minus the identity matrix over delta t as delta t goes to 0. This matrix q is called the infinitesimal generator, also called a transition rate matrix. And it turns to be important in the continuous time case. Q of t, in fact, consists of a matrix of those qij's at time t. And basically, Qij is the rate of moving from state I to state j at time t, namely over the next delta t seconds, divided by delta t. That's what this gives the rate here when you divide. And that's for I not equal to j, but for j equal to I, we use a special case, and we call that minus qii. It's the rate of leaving state I at time t. Now, going from this non-homogeneous case, we then drop down to the homogeneous case, in which case Q, this infinitesimal generator, does not depend upon time. The ij rates don't matter when it occurs. It's basically true at every point in time. So h of t is all you need. It's defined of h of s and t seconds later. The Forward-Chapman-Kolmogorov gives us a differential equation in terms of this now time-independent Q. The backward equation looks like this, and the solution to that equation is simply h of t is e to the qt, a matrix expression. No surprise that we get the exponential. Now, that was all about the transition probabilities. Let's talk about the state probabilities themselves. Pi sub j of t, it's the probability of being in state j at time t. We come up with this differential equation that the pi of t dt is pi of t times this infinitesimal generator q. For the irreducible case, we know that there's a limit, namely these pi j of t's, as t goes to infinity, get you an equilibrium set of numbers called pi j. And remember, the vector of pi j's we call pi, and then this equation becomes this equation because the differential of pi goes to 0. And pi goes to its limit, so we get pi q equals 0. That's somehow the continuous time analog of our good friend pi equals pi p, which we have yet to exploit in our coming work. Now, we took a particular case of continuous time, discrete state, homogeneous Markov chain, namely something called the birth-death process. The birth-death process is a birth rate lambda k, which means the rate is going from k to k plus 1, namely a new customer arrives or is born to the system. A death rate mu k, going from q to k to k minus 1. And basically what happens is the probability of a birth in the next delta t seconds is lambda k times delta t plus little o of delta t. And the probability of a death in the next delta t seconds, given you in a state k, is mu k delta t plus little o of delta t. And what we're really looking for is the thing we're continuously looking for. What's the probability of being in a given state at some time? The probability that x of t, the random variable, the process basically, puts you in state k. Now, we then began to write down the equations regarding that by conserving rate of probability across a state. And we ended up with this equation last time. We're in the middle of deriving a solution. We came to this point that the pk of t plus delta t is described in terms of itself, the state 1 less and the state 1 more. And the next equation we needed was the one for k equals 0. This is for k greater than equal to 0, or greater than equal to 1. For k equals 0, the same argument gives us the following, that p sub 0 of t plus delta t is equal to, look up at this equation above, instead of k, we get 0, so it's p0 of t minus, essentially, the ways out of that state. Now, you can't have a death when you're in state 0, so you're going to get, essentially, this term without the death parameter, mu. Namely, we're going to get minus lambda sub 0, that's what the k is, delta t, p sub 0 of t, plus the other terms. Now, there's no, essentially, no, this state does not exist. So we go to the next terms, and we're going to get, when k is 0, we get a mu 1 times delta t, p sub 1 of t, namely a death from state 1, and all of that plus little o of delta t. Okay, now let's solve this. As usual, we have now an expression. Let's solve each of those basically for what's going to be a differential. So up here we're going to take this term, subtract itself out, and divide the whole thing by delta t. Namely, I'm going to take p sub k of t plus delta t minus value an instant ago, p sub k of t, and I'll divide ahead of time by delta t. The whole thing will be divided. And on the right-hand side, I'm going to get that minus lambda k plus mu k. The delta t went away, I divided by it, left with pk of t. Similarly, the next term I get plus lambda k minus 1, pk minus 1 of t. And then I'm left with the mu k term, plus mu k plus 1, pk plus 1 of t. And all of that, the little o of delta t didn't disappear, but remember I'm dividing by delta t all throughout. And similarly, the term for p0 is the following. You can write that down by inspection almost. p0 of t plus delta t minus p0 of t itself divided by delta t. And we're going to miss some of those terms as before. We get a minus lambda 0 p0 of t plus mu 1 p1 of t plus again little o of delta t over delta t. Now, what do you think the next step is in both of those equations? This was for k greater than or equal to 1. What's the next step, anybody? Yes.
I had a question.
Oh, question, yes.
And maybe you talked about this last time. Can you address that O of delta t kind of gets us into a sheet and kind of the loose upper bound of delta t over delta t. Is that correct?
O of delta t lives by itself.
Okay.
O of t literally means any function that goes to 0 faster than delta t. For example, it could be delta t squared. Faster than delta, that's all it means. So with where did it come from? We did an expansion with 1 minus lambda k delta t minus something times delta t squared, kind of Taylor series. Those terms, delta t squared goes to 0 faster than delta t. So does delta t cubed. All of those I lump into this term, little o of delta t, to get rid of them all and just, but don't forget about them, because we're trying to be more rigorous than you would if you neglected it. So that's all a little o of delta t means. So back to my question. You can't get away with it. What is the next step in this expression? What would you do with these terms I have over here? For example, what is this begging you to do? Yes, take the limit as delta t goes to 0 to get a differential. So let's do that, okay? So we're going to take the limit as delta t goes to 0 for the entire equation. And what do we get? We're going to get the following. The one on top is going to be the differential of pk of t. Good old differential calculus. Is equal now, delta t goes to 0. These first two terms have no delta t's in them, so they just repeat. In fact, so is true for this term. But what happens to O of delta t divided by delta t? As delta t goes to 0, O goes to 0 faster than delta t, so the whole thing I just circled goes to 0. So I get rid of it as delta t goes to 0. So let's write that out. So continuing on, these terms don't change, minus lambda k plus mu k pk of t. And remember, I started this discussion last lecture by saying I'm going to torture you by making you to go through what I'm just doing right now for a good reason. I want you to feel the pain. Plus lambda k minus 1 pk minus 1 of t plus mu k plus 1 pk plus 1 of t. And the last term is missing, O of delta t over delta t goes to 0. This is for k greater than or equal to 1. And for the 0 term, we get the derivative p0 of t dt equals minus lambda 0 p0 of t plus mu 1 p1 of t. And that's for the case k equals 0. So there we are. We're not done. We haven't solved this equation. Pray tell, what kind of equations am I looking at here? To me, it looks like a differential equation, and it looks like a difference equation on k. So it's that differential difference equation I warned you about when we studied basically transforms. Now we're ready to use our wonderful tools, okay? This is equivalent to a system we saw earlier using different notation. I'm going to write it down. We had shown that d, when we're using the pi j notation, d pi j of t dt was equal to qjj pi j of t plus the sum over all k not equal to j of qkj pi k of t. We had that earlier in last session. And this one makes sense. The qjj means you're going from j to j. So basically that probability remains. And qkj is basically moving stuff in and out. Okay. Now we also need initial conditions if we're going to solve this set. Remember, this is simply for the birth-death process. So we need p sub k of 0 for all k's. K equals 0, 1, 2. You have to tell me what's the probability in being in any state at time 0 to get this thing started. We're looking for a transient solution. pk of t is the transient solution. What's the probability of being in state k at any time t from time 0 on to the future? And we also need, as always, that the summation of these guys goes to 1. Summation pk of t is equal to 1 at any time. That's from k equals 0 to infinity. So there you are. Big homework problem, go solve it. Okay? Well, comes the reprieve for the prisoner here. I'm going to say wait. We could have found this much easier. We could have found these equations up here. Let me give a name to the set of equations. I'm going to call that equation 14. We could have found the equations 14, believe it or not, by inspection. And I've already clued you into what that inspection method is. Much more than all the aggravation we did toward the end of the last lecture and the beginning of this one. All the torture I put you through could have been and will be avoided. Okay? Namely, let's just use the state transition diagram. So let's look at the state. Let's look at state EK, being in state K. Let's recognize there's ways in and there's ways out of that state. And if that's state K, we could have come there from state I and go to K, all the way down to, say, I'll call it I sub 1 K, down to, say, Q sub I n K. N is an arbitrary index. From any other state, we could have gone in, and we can go out to a bunch of other states. From K to some other one, let's call it J1, down to Q sub K, J sub M, arbitrary indices. And by the way, this self loop, namely Q sub KK, is omitted. We agreed what goes in comes out to yourself, so we don't need to count for that. Remember, the QKKs had a special notation. It was summing. It was a negative sum of everything on the kth row of the matrix. And if I basically recognize what goes in, comes out, and if it's not in equilibrium, it accumulates in EK, difference between in and out. Now, in order to do this for the birth-death system, what I've drawn here is an arbitrary Markov chain. Let's do it for the birth-death system. So I'm going to identify a number of states. Let's do it over here. One state, another state, another state, a whole sequence of states. I'm going to label these states. We'll start with state 0, then to state 1, then to state 2, then eventually to state K minus 1, state K, K plus 1, and on. And now what kinds of transitions are allowed here? It's a birth-death process. So from state 0, where can I go? Birth-death. I could stay at 0, which we ignore because how fast do I stay in my current state? At an infinite rate. I keep cycling until boop, I pop out. So I want to see the pop out. So where do I go from 0? As you said, Rohit, state 1. A birth occurs. And at what rate does that happen? Remember, these are rates. Let me point that out carefully. These are rates, not probabilities. Now it's continuous time. Lambda what? Lambda 0, that's right. This is rate lambda 0. And for state 1, where can I go? Exactly. I can go back to 0 with a death at a rate what? Mu sub 1. Oops. Or I can go up to state 2 with a birth at what rate? Lambda 1. And so the picture continues. Let's start to draw the rest of it now. What I'm drawing is a state diagram, which is always the thing to do to give you an idea what's going on. You either go up 1 or down 1 from every state. That's what birth-death means. It's a particular case we're looking at. A rather important case, in fact. Okay, now let's look at state K. I can go into state K from the state below at a rate lambda sub K minus 1. I can go out of state K by going up at a rate lambda K, or going down at a rate mu K. I can enter it, as say, from below. I can enter from above at a rate mu K plus 1. So that's pretty much the full description. Now, what I've just drawn there contains the same information as the Q matrix, which we know we need to solve the system. But I want to write down the equations by inspection instead of the torture I took you through before. The flow rate into a state minus the flow rate out of the state is the rate at which probability accumulates in that state. So let's write that down. The flow rate into EK at time t is equal to, well, again, how much is flowing into K? From below, whatever is coming at a rate lambda K minus 1. That's the rate. But how much was there to come from? It's whatever state K minus 1 had. It had some probability, and it's flowing out. So I'll multiply by the amount of probability was there, pk minus 1 of t. Similarly, from above, I'm coming in at a rate mu k plus 1. How much was there in that state, ek plus 1? An amount pk plus 1. And similarly, the flow rate out of ek is equal to, well, there's two ways out. It's lambda k plus mu k of how much? How much it has, which is pk of t. All this at time t. So the difference is the rate at which it accumulates. Its rate of accumulation. Namely, the rate at which probability is accumulating in state k at time t is dpk of t dt, and that's equal to the difference what I just said. The rate in is lambda k minus 1 pk minus 1 of t plus mu k plus 1 pk plus 1 of t minus the rate out, which is minus lambda k plus mu k pk of t. If we look above now, if we look at equation 14, isn't that exactly what I wrote up here? It's exactly that equation that I'm circling now, and I got it by inspection. Directly from this state diagram that I drew. And of course, do the same thing with state 0. Namely, you look at state 0 and see what comes in and goes out, and the accumulation state. So in some sense, to summarize, what we did is, just a moment. Okay. We simply drew an imaginary boundary around EK and looked at the rate in minus rate out equals to rate equals to growth. rate in minus rate out equals rate of growth. Now I will remind you that that was a picture we saw before very early. Let me see if I have a copy of it here. I don't have a copy. I'll just do it again. If you remember, I had that picture. There was a flow system for gallons of water, stuff coming in at some rate, f sub I of t, leaving at a rate f sub O of t, and the amount that's accumulated in here, f sub s of t, was the difference between those two rates. That's a general picture. This is a very simple example of that. In fact, if you go a little further up, this EK picture I drew is exactly the same thing. We have a special case, it's only birth-death. This was for a more general case. But notice what I'm saying is still true. It'll apply even if it's more complicated than birth-death. So you can write these equations down by inspection. Now, in the limit, as t goes to infinity, and assuming a steady state exists, namely recurrent non-null systems, then we're going to get no accumulation, so the differential is 0, and that will equal lambda k minus 1 times little p sub k minus 1, the equilibrium distribution, don't put a t on it, it's gone to infinity, plus mu k plus 1, little p k plus 1, and then subtract out what's going out, which is minus lambda k plus mu k pk. And that's a set of equations we're going to solve. But in fact, what is that set of equations? That's simply the equation that says pi q equals 0. In discrete time, remember that was pi equals pi p. In continuous time, q replaces p, and the differential is 0. And so I've hinted that this approach works more than just for the birth-death process. We could have drawn a boundary around any set of states. So let me copy this diagram I had up here. I'm cheating because you can't do this as easily as I can. What I basically did was draw a boundary of various fit. For example, I drew a boundary around the state k, this red boundary, and I said flow in minus flow out equals rate of accumulation inside. And I did that for every state, right? I did that for k, k minus 1, for every state in the system. And they all look the same except for state 0, which has no stuff coming in from below. That was that special case for k equals 0. So I'm repeating over and over again what I did. I made sure that the flow in minus flow out is the accumulation. Now, there's something else I can observe here. And let me say the following. I could have drawn it around any set of states. I could draw a boundary around any set of states, and the same idea applies. The one I chose for the example we used was to draw a boundary around individual states. But in some other color, let's say blue, I could have started, say, with state 0. That's one of them. Oops, let me use my pretty capability here. And the next one I could have done was to include 0 and 1 together. And after that, 0, 1, and 2 together. And on up. I mean, why not? It holds there. For example, for the second blue circle, I would simply say lambda 1 times P1 plus whatever's coming in from this thing, namely it'll be lambda 3 out of P3, etc. So I get a set of equations. It's all true. But there's a condition. In case I'm careless, suppose I circled the red around 0, the red around 1, and the blue around 0 and 1. In some sense, I haven't added anything new. It'll be a dependent equation. So the condition is, first of all, what I did was do each state separately. That's what we did. Second, do any state but include a new state each time. If I did blue around 0, then blue around 1, then blue around 0 and 1, I haven't included a new state. That equation would be dependent on the first two. But if I keep including a new state somehow, doesn't have to be the blue, it could be green, whatever collection, you could do it yourself. And of course, we always need summation of the probabilities goes to 1. Now, what I've just described, this is what we call the inspection technique. And it is as simply as inspection. And it gets you to the differential difference equations very simply. Now, this is good for any Markov process in general. It didn't have to be a birth-death process. In fact, it's also true for semi-Markov processes. The same idea will apply. The flow rate equation, that very lovely diagram I drew very early, a couple of sessions ago, this one up here, applies. It's a very simple law of physics, if you will. Now, it turns out that the birth-death systems, the birth-death model, can generate many interesting queuing systems. And we'll go through them a little bit later. In fact, the next chapter in the book, I believe it's chapter 3, is all about birth-death Markovian cues. And by that I mean, when I say interesting, I mean we can solve them. In general, though, for an arbitrary Markov chain, we may be able to write down these differential difference equations. Let's look at the differential ones, number 14. But we won't necessarily be able to solve them. But we can write down the conditions. And by the way, remember, there's a unique solution, so if you can guess the solution, plug it in and see if it satisfies these equations. But in general, that's difficult. And I'll give you an example later of some difficulties. But in the case of birth-death, there's a whole family of interesting cases. So I'm going to give you a yet more special birth-death system. I'm going to go through some examples now. And see where that leads us. First thing I'm going to do is talk about a pure birth system. Let me call that number 1. I'll even go so far as to color it in. This is going to be the pure birth system. No deaths. So what does that mean? It means that there's no death rates. Namely, assume that mu sub k equals 0 for all k. No deaths. Now what does that mean? Let me go back to something we've seen before. Remember this picture here. I gave you this general stochastic process picture to give you an idea where we're going. Where we've been is we jumped rather quickly into Markov processes, discrete and continuous time. Just now we've been talking about birth-death processes, but now I'm going to take you to the pure birth process, which says, as is shown here, that the death rate is 0. So what's general about this case and what's specific? What's specific is it's going to give us an exponential time-in system, as we're going to show, but it allows the birth rate to change according to the state you're in. Okay? But I'm going to take you beyond that right now and relax that assumption as well. I'm going to now further assume, because it's an important case, that lambda k equals a constant number lambda for all k. Which means in this picture, I've now taken us into this inner circle, which you see says all the lambdas are the same. Now it shouldn't surprise you that that's a very special case. It's the innermost circle of all of these processes. Every one I've drawn there has this as a special case. And I've given it a name, the Poisson process, as we'll see, but it's especially interesting And that's where I've driven you right into the inner circle. And I think this picture helps you understand the excursion we've taken and where we're going now. Okay. So having said that, let's draw the picture. And I'm going to draw the state diagram. And I'm going to just draw a few states here. I'm going to draw state k minus 1, k plus 1, and of course the transitions are from k minus 1 I can go to k, from k I go to k plus 1 on up, below k minus 1 into it. But there's no way down. Does this have an equilibrium solution? Is it a recurrent, non-null set of states? Or what is it? No state remains. If you're in a state, you eventually leave it, you never come back. So these are certainly not recurrent non-null. It's not going to be an equilibrium solution. Okay, but nevertheless we want to study it. So let's write down the equation by doing what? By circling the state. And by the way, I didn't label these arrows. They're all lambda. Whoops, go with that in black. Lambda, 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 etc. So let's write down the time-dependent equation. d sub p k of t dt, the rate at which probability accumulates in state k, is the rate at which it comes in from where? From state k minus 1 at what rate? Lambda. Lambda sub pk minus 1 of t. And it loses what it had at a rate lambda also, minus lambda pk of t. And that's for k greater than equal to 1. And it's easy to write down the zeroth equation, dp0 of t dt equals, well, there's no way in from below. There's no state minus 1. So simply minus lambda p0 of t. Before we try to attack this, look how easy it was to write down that differential difference equation by inspection. That's the beauty of this inspection technique. We're going to take exquisite advantage of it as we go along. Now, what else do I need? I need initial conditions. The initial condition I'm going to take is the following. I'm going to assume that we start off basically for sure in state 0, namely p sub k at time 0 is equal to 1 for state 0 and 0, k not equal to 0. Namely, with 100% of the time, I start off with nobody in no births, nobody in the population. By the way, what other equation do I need? I haven't written it down. There's another equation I need if I'm going to solve this baby. I've told you over and over again. This does not have an explicit solution unless I do something else for these probabilities. Sums to 1, exactly. I need the summation of the pKs at any point in time must go to 1. Don't forget that one, because sometimes you end up with a constant you can't resolve, and that's the way to resolve it. Okay, so let's solve this. Let's solve this. First of all, for p0 of t. Remember, now I'm faced with a set of differential difference equations. I can solve it a number of different ways. I'm going to solve this in a rather straightforward way. So the first thing I want to do is solve this equation. Well, I don't have to go to differential equations to solve that. I know the solution to that. What is it? You've seen this in elementary calculus. P0 of t is going to equal to e to the minus lambda t. Simple first order linear differential equation. Now let's take that. Well, let's take that and let's start iterating it on the top equation. But no surprise, the first hour is over, so let's stop and we'll continue in 10 minutes. Mic on? Yeah, okay. Hello? Hello? Yeah. You want this back on here? Why not? Yep. Okay. Okay, why don't we continue the lecture now? We've gotten to this first equation for P0 of t from the set of equations we derived trivially for this simple pure birth-death process. Next step now will be to plug in P0 of t into the equation on top of the page. Okay? If you do that, you'll get, for k equals 1, dp1 of t dt is equal to lambda p0 of t minus lambda p1 of t. But we know what p0 of t, we can plug it in, do a simple solution, and we'll find that p1 of t equals lambda t e to the minus lambda t. Now, if you didn't believe me and I just threw that at you, how could you check it? What would you do to check that this last thing I wrote down is correct? Well, just plug it back into this equation. You know the P1, you know the P0, and of course it's correct. Okay. Now, if we continue that by induction or any other method you like, gives the solution as follows. Is that P sub k of t for this pure birth equation is equal to lambda t to the k over k factorial e to the minus lambda t. And that's for k greater than or equal to 0 and t greater than or equal to 0. So let me circle that because that's an important equation. I'll drop this a little bit so I can properly circle it. Now, if you recognize this equation, that's a Poisson process. This pure birth system, it constitutes a Poisson process. These are equivalent. So let's see what that looks like. Let's see what that equation looks like. Notice it depends upon t and depends upon k. So let's pull up a picture of this thing. That's what that two-dimensional function looks like. And notice we have k going in this direction, and essentially t going in this axis, and the function we're after, pk of t, in this direction. So if you look at any particular value of k, and you try to observe what happens to the probability of being in state 2 at time t, it starts off with 0. Why? Because we started off up here for probability 1, we're in state 0. And it grows like this, and it falls off, and eventually where does it go? It goes to 0. Okay, but more interestingly, there is something called the Poisson distribution. The label of it says so here. We're familiar with called the Poisson distribution. What I have above is a Poisson process, you notice, as a function of time. The Poisson distribution, of course related to this, describes a random variable x whose basically distribution as follows. The probability that a random variable takes on the value k is simply lambda to the k over k factorial e to the minus lambda k. That's the Poisson distribution for all k. Namely, at a given t, this is how the number distributes. And let's plot that here. Let's take a particular t, say this one here, and pass it over various values of k. Now for k equals 0, we get this much. For k equals 1, we get that much, etc. This is more or less the more familiar Poisson distribution you've seen in the past. That's the probability at a given time, what's the distribution of the number in the system. Now, I'm going to draw you a picture of that a little more carefully now. Sorry, it's not as big as it could be, but there's an example of the Poisson distribution for various values of lambda. In other words, it's taken this red line I drew and taken different time slices. So you see for a small lambda, you get this black curve, the solid black with the orange dots. You get the purple dots if you move a little further out in time, or continue out in time. In the blue dots, you've gone further down. This is basically a probability mass function that I'm showing you here. And what do you notice about these curves? Any comment about what those curves look like, especially the blue one? Does it look semi-familiar? It looks like a Gaussian, exactly. This basically goes to a discrete Gaussian. Due to our good friend, the law of large numbers. Basically, we're asking, for the blue curves, t is large. In a long time, we're going to get many births. And what's the addition of the distribution? It's adding together those birth times, if you will. So it looks like you're adding together a large number of independent random variables, independent births. No surprise it goes Gaussian, independent of the original distribution of how those births came about. Okay, so this is all consistent. I don't want you to confuse the black curve here above as a function of t with the curve down below, which is a function of k, which I've drawn in red in the upper curve. Okay. Now we're going to use the Poisson process, this thing I've described up here, quite a bit. So let's talk some more about it. This Poisson process and by the way, I still owe you pictures of these people like Poisson and Chapman and Kolmogorov and Laplace and de Moivre and all the rest. We'll get to them later. But this person really existed. And by the way, if you know French, the word Poisson, his name, means fish. And so I like to make the lovely, I wrote a poem about a Q one time, and I talk about fishing in a Poisson stream. Now a stream is a random process. So it's playing on words 3 different ways here. But anyway, Poisson process, okay? It's common in nature and, of course, in physics. It occurs all over the place. Basically, it's the sum of a large number of independent stationary renewal processes. With an arbitrary distribution for each. Renewal process. That sum leads to a Poisson process. That's what I'm saying here. For example, the number of soldiers in the Prussian army who were kicked in the head by their horses has a Poisson distribution over many, many counts. The number of telephone calls coming into a telephone exchange over time behaves like a Poisson process. And again, the fact that the sum of a large number of independent renewal processes is the same thing. That's a very lovely result. You take any renewal process, take a whole bunch of them, they can all be different statistics. Take a whole bunch of them and add them together, and collectively they look like this Poisson process. So it occurs often enough in nature. And we're going to use the Poisson process as an example of the way customers arrive to a queuing if you have a large number of independent arrival streams coming in, collectively, from this theorem, they look like a Poisson process. It's often assumed in queuing theory. It's often criticized. How come you're assuming a Poisson process? Well, it's true often. It's certainly true for telephone calls arriving. But it may not be true in some other situations. So you can argue it's a good and bad assumption. Question?
Yeah, did you define renewal process? It seems self-evident, but just can you talk about that?
Yes, we did. And we can go back about 3 lectures when I did random processes. And it occurs, let me show you the picture up here. Basically, a random walk is a semi-Markov process where you're basically accounting where you are as you hop from state to state. And you're always increasing. Okay, you're going up a chain. 1, 2, 3, 4. Where are you at a certain time? What's the probability you go from state I to state J for an arbitrary time between hops. That's why basically it's not a Markov process. A renewal process is the same thing, but you're basically counting how long it took you to get there. Instead of the state, right. And again, you basically go one at a time and an arbitrary distribution again. Okay. Okay. So I say we often use this as the arrival process for queuing systems. If you recall, the notation for queuing systems was A/B/M and something about the amount of storage and number of number of people in the population. Often, this arrival process we replace by the symbol M, which stands for Markovian or memoryless. That means a Poisson arrival process. So we study plenty of systems where there's an M in that first slot. Just giving you a little heads up. There are chapters devoted to that. Okay. Now lambda is the average arrival rate in this pure birth system, the one we've been studying, this one up here. Pure birth system. Lambda is the arrival rate, the average rate at which customers arrive. Remember that. Notice I'm changing my notation a little bit. Instead of saying the average rate of births, I'm talking about the average rate at which customers arrive. I'm getting you warmed up to using the terminology of queuing systems. A birth to a queuing system is an arrival to that system. A new customer comes in. A new one enters, okay? P sub k of t, what we just solved for, is the probability of k arrivals in the interval 0 to t. Remember what P sub k of t was for our process. It was the probability of having k in the system at time t, starting at time 0. So over an interval of t seconds, P sub k of t is the probability of getting k arrivals. Now again, we have lambda customers. I'm trying to introduce the notation of queuing systems. Lambda customers per second, which implies that the average number of arrivals in the interval 0 to t is how much? Over t seconds, you get lambda per second. So how many you get overall in t seconds? Clearly lambda t. That's just intuition and argumentation. Let's prove this. Let's prove that intuitive statement. Because we now know the distribution of P sub k of t. So let k equal the random variable represent the number of arrivals in the interval 0 to t. And the expected value of k, which is what I'm looking for, is clearly the summation of k times its probability, pk of t. So let's plug in for our solution up here for the Poisson process, this boxed equation here. And I'm going to take that which doesn't depend upon k outside, namely the e to the minus lambda t part of it. And under the sum, I'm going to get k times what's left, which is lambda t to the k over k factorial. Which trivially now, let's spend a little bit of time. It's lambda e to the minus lambda t. I'm going to take one lambda t out, and then what I left inside, k equals now 1 to infinity, because I've got k over k minus 1 factorial. So upstairs I get lambda t to the k, that was there, and k over k factorial gives me downstairs k minus 1 factorial. So I don't need the 0th term. This sum, replace k by a new variable that starts at 0. I'll call it k again for fun. From 0 to infinity of lambda t to the k. I'm sorry, this is a k minus 1 in the equation above. I pulled one out. Lambda t to the k over k factorial. And what is that sum that I just formed? It's e to the lambda t by definition. So this whole thing is simply lambda t, as I argued at the top of the page. So expected value of the number of arrivals in t seconds is lambda t. For a Poisson process. Let's go for the variance now. Oops. First, I'm going to calculate something related to the variance. I'm going to go after the expected value of k times k minus 1. And you probably suspect why I've done that. That's not quite the variance, but it's going to be useful for the variance. That's a summation of the random variable little k times little k minus 1 times the probability associated with that, which is pk of t, which is equal to, take out the e to the minus lambda t, take out lambda t squared, you'll see why in a moment. I'm left with the summation that was originally from 0 to infinity. Now I'm going to go from 2 to infinity because the other terms disappear, of k times k minus 1, lambda t to the k minus 2, I took 2 of them out, over k factorial. But what is this? K minus 1 times k over k factorial gives me k minus 2 factorial. So I got lambda t to the k minus 2 over k factorial from 2. So that whole thing is a summation, once again, of lambda t to the k over k factorial from 0 to infinity, which we know is e to the lambda t. Therefore, this expected value of k times k minus 1 is just lambda t squared. Having done that, the variance for k, we know, is the second moment minus the first moment squared. Expected value of k squared minus the square of expected value of k. And that's equal to, and you actually needed this or will need it for the homework, I forget which one. Expected value of k squared is expected value of k times k minus 1. But now I've subtracted out the expected value of k from k squared, so let's add it back in. plus the expected value of k, and all of that minus the square of the mean value. You got to be careful where the brackets and the squares go. Now, I know all of this. I just found the first term is lambda t squared. By the way, that's quantity, lambda t squared. Plus expected value of k, which is lambda t, minus the square of that, minus lambda t squared, which is just lambda t. That's this plus sign here, I'm sorry. It's just lambda t. So the variance for the Poisson process is lambda t, the same as the mean, which is interesting. Let's go a little further. This is an important process. I want to study it a little bit more now. Let's take the Z transform of the probability associated with k, namely I'm going to call it G sub k. What is that? That's the probability the random variable k equals k. So G of Z, which is the Z transform I'm talking about, is equal to expected value, as always, of Z to the random variable k, by definition, which is the summation of gk z to the k and this only works for absolute value of z less than 1. So let's plug in for the gk. Gk is what I want, is pk of t. It's z to the k pk of t. That's what I mean by gk. Let's plug in the exact value. That'll be the summation e to the minus lambda t. And let's put a z to the k inside the power to the k. I had lambda t to the k times z to the k, so lambda tz to the k over k factorial, which is equal to e to the minus lambda t upstairs plus lambda t z. So finally, G of z, the Z transform, the Poisson distribution, which again is equal to expected value of z to the k, just to remind you, is equal to e to the lambda t times the quantity z minus 1. Let's remember that. We're going to use that occasionally. So now we have the mean and the variance of the Poisson process, its distribution pk of t, and its Z transform. Well, just for fun, and you may or may not consider this fun, let's recalculate the mean and variance of k from its transform. Okay, the usual way. So I want to recalculate. Again, I think I told you last time, these few lectures we're going through, we're going to show you a number of different ways to do the same thing. The inspection method was one way to do the more difficult delta t argument. Here I'm showing you many ways, reminding you many ways to get the mean and variance and the moments. So let's do that. I want to recalculate the mean of k and the variance of k. We already know what it is. Let's check. So g prime, first derivative, at z equals 1, we know is the partial with respect to z of the expected value of z to the k, which of course is expected value of k. We know that from our moment generating properties. So using the Z transform, the expected value of k, differentiating, we're going to get basically lambda t, remember, of the z transform, and z transform up top, so we get lambda t e to the lambda t z minus 1, except we have to put z equal to 1, according to this expression here, z equals 1 here. And this whole thing is equal to lambda t. Right, we did that before. Okay. The variance in terms of the z transform is the second moment, this is the second derivative at z equals 1 plus the first moment at z equals 1. All of that minus the square of the first. Similar to what we had above. So let's plug in. The second derivative of g is going to give me lambda t squared when I differentiate the expression in red twice. I'm left with e to the lambda t z minus 1. All of that at z equals 1. Plus the first one I just cooked above with the check mark, that's lambda t minus lambda t squared. Well, if I set z equal to 1 in the first term, I get lambda t squared that cancels with the minus lambda t squared. And what do I get? Of course, lambda t again, as I should, check mark. So just exercising some of the tools you already had. This boxed equation we're going to use over and over again, the z transform of the Poisson process. Okay. Now we know something else, by the way. We know that if we get k arrivals in the interval 0 to t from a Poisson process, then the joint distribution of those arrivals, of those instants when the arrivals occur, is the same as the distribution you would have if you chose k points in that interval uniformly. In other words, if you have the interval, here's an interval from 0 to t, and you throw k arrivals in here from a Poisson process, they're going to hit certain places. And suppose you know that k came in there. It turns out that's the same distribution as if you uniformly allowed k arrivals to come uniformly over this interval. I'll draw that in red. Suppose there was a uniform distribution of picking the time when an arrival occurs. That would have a probability of 1 over t. Just throw them in there by that. The statistics of where they fall in the uniform distribution case is the same as the Poisson. Okay, I haven't proven that. Okay, but I'm going to prove something else. I'm going to basically say that this is somehow related to the exponential. Okay? By the way, the Poisson process has a lot of amazing properties, and this is just one of them. So let's do a little calculation. Let the random variable t with the tilde above it be a random variable as the time between adjacent arrivals say to a queuing system. We typically talk about the inter-arrival time distribution. Well, we know what its capital PDF, it's its distribution function. That's capital A of t. And the density, little pdf, the probability density function, we denote as little a of t. Again, I'm playing with this because I want to get you familiar with the idea of the notation for queuing systems. And we know that a of t, capital A of t, is defined to be the probability that that random variable t tilde is less than or equal to t. That's what I mean by capital distribution. And that's equal to 1 minus the probability that it's greater than t. Now, what is this probability of t tilde greater than t mean? It means there's no arrivals in the interval 0 to t. If the interarrival time is bigger than t, then nobody occurred up to t. And what do we call that? We call that P0 of t, probability of no arrivals in t from a Poisson process. So the A of t we have is equal to 1 minus P0 of t from the Poisson process, but we know what P0 of t is from above. That's 1 minus e to the minus lambda t. And that's for t greater than or equal to 0, of course. And if that's the case, then little a of t, its density, is simply lambda e to the minus lambda t. Again, t greater than or equal to 0. Well, remember, I introduced the Poisson process when I substituted for this. That came from the Poisson process. And when I did that, I got this, which means that the interarrival time is an exponential, which means they're the same thing. If arrivals come into a Poisson, according to a Poisson process, the time between arrivals has a density function which is exponential. So I'm just going to write that, if you will, in words. Poisson arrivals is the same as exponential interarrivals. Now, I claim that's memoryless, that the exponential distribution is memoryless, and I've said that a number of times. I've yet to prove it, by the way. But if it is memoryless, what I mean by that, I haven't proven that it's the case, means the past history of the random variable has no role in predicting the future of that random variable. Well, let's see what I can prove about this. Let's calculate the following. Let's calculate the probability that the random variable t tilde is less than or equal to t plus some known number t0, given that the interarrival time is known to be greater than t0. In other words, I want to ask, what's the probability that it takes t more seconds before an arrival comes, knowing that for the first t0 seconds, nobody arrived? And what do you think I'm going to try to prove about this? If the statement above about memoryless is true, then knowing how long it's been since the last arrival shouldn't affect this probability, namely that it takes t more seconds. That's what I mean by memoryless. So let's set out to do that. Let's write this out. Well, this, using the definition of conditional probability, a good friend, is the following. Well, before conditional, this is the probability. This basically says that it's lying between t0 and t plus t0. So t0 is less than the random variable t tilde is less than or equal to t plus t0. I have to divide by the condition, which is the probability that t tilde is greater than t0. Now that is equal to the following. The numerator is equal to the probability that it's less than t plus t0 minus the probability that it's less than t0. So the probability that t tilde is less than or equal to t plus t0 minus the probability it's basically less than or equal to t0. Let's look at that. What's the probability is less than or equal to t plus t0? Something. Take away the probability it didn't occur by t0. The difference is the probability it occurred between t0 and t plus t0. And downstairs I got my good friend, probability t tilde greater than t0. Now, as I did in the equation at the top of the page here, I'm going to say probability t less than or equal to is 1 minus probability greater than. And I know what that function is. Basically, it's, remember, it's a Poisson process. So what's the probability t tilde is less than or equal to some number? It's 1 minus e to the minus lambda t plus t0. Remember, this is a Poisson process. I know that. All of that minus the term on the right, which is again similarly 1 minus e to the minus lambda t0. And downstairs, I got the probability t greater than or equal to 0, which I can write as 1 minus e to the minus lambda t0. Now, I got some obvious cancellations. The ones upstairs cancel. The ones downstairs cancel. And what I'm left with is equal to e to the minus lambda t0 times a bracket, which is 1 minus e to the minus lambda t. And downstairs, I've got e to the minus lambda t0, which gives me what? Simply 1 minus e to the minus lambda t. So it's independent of t0. Knowing how long it's been since the last arrival doesn't affect how long it takes from here on. T seconds more is as if I never knew that. So therefore, it's memoryless. And now I've got an interesting triplet. triplet is this. I've got Poisson arrivals, one idea. I've got constant birth rate from which it came. And I've got exponential interarrival times. And all of those imply each other. It's a three-way equivalence. You say one, you get the other two. And that's some of the magic about Poisson arrivals. Okay, that's an important thing to keep in mind. I'm going to show you something else now related to that. I want to focus on the exponential distribution. So I want to draw the exponential distribution, the density function. This is versus t. I want little a of t. Let's look at the density. And let's draw the exponential. That function is what? It's lambda e to the minus lambda t. That's the interarrival time density. Now suppose I told you that it's been t0 seconds since the last arrival and nobody's come in. What's the distribution of time until the next arrival? So if you look here, you know, somehow it's related to this cross-hatched area. That's what the future looks like from here on. But there's a condition in the crosshatch I just wrote, namely, it's the probability nobody occurred for t0 seconds. It's a condition, and when you look at a sample space with a condition, you have to normalize that sample space by the probability of a condition. So I have to basically divide by the appropriate probability. What happens when it means scaling up the rest of that curve so its integral still equals 1. And that means when I scale it up, it looks like that. And the equation for that expression is lambda, let me write that more carefully. That's lambda e to the minus lambda t minus t0. The point is that the red is same curve as the black. Another way to say that is the tail of an exponential looks exactly like the whole exponential. And it's the only continuous function with that property. It's a unique function. In fact, it may remind you that way back when we studied essentially linear systems, linear time invariant systems, that exponentials appeared as the eigenfunction of the system. It's not unrelated to this fact, by the way. So to write it in words, the exponential is the unique continuous distribution whose tail is itself. So again, if you know it's been t0 seconds, you look into the future. The future, the red, looks exactly like it did from time 0. So the future looks the same no matter how long it's been. So knowing how long it's been doesn't affect your prediction of the future. Very important. So for the exponential, as opposed to the Poisson, let's find some numbers. Let's find the mean. Namely, I want the expected value of this time between interarrival time. And we use notation t bar for that. And obviously that's equal to the integral from 0 to infinity of t times a of t dt which is equal to the integral, let's plug in t lambda e to the minus lambda t dt, which equals, and we'd used this trick so many times before, it's minus lambda times a partial with respect to lambda of the integral of lambda e to the minus lambda t, excuse me, just e to the minus lambda t dt. Differentiate to lambda, you get a minus t coming down, the minus cancel, you get the lambda that you needed. And you've done this enough times in homework. So if you do that calculation, you find out that it's equal to 1 over lambda. And differentiate this thing, you get the lambda downstairs. Okay. So t bar is equal, the mean interarrival time is 1 over lambda. The arrival rate is lambda. And if you do the variance, sigma squared sub t tilde, clearly it's equal to expected value of t squared minus t bar itself squared. You're going to find that this quantity, if you do a calculation just like above, you get 2 over lambda squared. This is 1 over lambda squared. And so the variance of the exponential is 1 over lambda squared. Let's circle that, and we'll be done in just a moment. And now we can recalculate that by the transform. We'll do that next period. And we'll calculate something else related to this, basically called a coefficient of variation. But let's terminate now. See you on Wednesday. Thank you very much.